and welcome back to another video on Spark optimization techniques. This is the fourth video in the series of our optimization techniques that we are discussing. So we already talked about spill and skew. So if in case you did not get a chance to look into the previous videos and want to know or get an idea about how skew and spill works and how you can optimize those operations in Spark, so please do watch that video. And today we are here talking about shuffle. So shuffle is a very critical operation in Spark. I mean, to be honest, we cannot avoid shuffle. I mean, we can avoid shuffle if we just rely on the narrow transformations, but that's not usually the case when we work in production environment. So shuffle gonna be there. The only thing that we can do is to reduce it so we don't actually transfer data across the cluster. So we're gonna discuss in this video how shuffle works, why it happens, why it's expensive, and how you can tackle it while working in the Spark environment. So what is shuffle, right? So shuffle, it's the process of redistributing data across the cluster. It's actually moving the data across the cluster. It happens during operations like group by key, reduce by key, join, or distinct. This involves sorting and transferring data over the network. So this is to summarize, this is nothing but when you perform an operation where Spark has to know which data belongs to which partition. So it's gonna usually transfer this data to make sure that what it's computing is actually available. We're gonna discuss how shuffle works with a very small simulation. So this is a Spark cluster, let's say, with two node 1 and node 2, and 4 partitions, partition 1, partition 2. Actually, on node 2, it's going to be partition 3 and partition 4. But I think for the simulation, it's fine. So we have 2 node and 4 partitions. Now, let's say I'm applying an operation, right? So since Spark is a distributed computing framework, it's gonna copy this code or the logic to each of the partition, right? Or the task, I would say. So let's say we are applying a distinct or join or group by whatever. So we perform an operation, and now let's say this operation generates shuffle. So now what is Spark gonna do? It's gonna, fly this data, or to say redistribute this data across the partitions in order to perform this join or distinct or group by operation in a correct manner. So this shuffle or redistribution of data is what we are discussing. And of course, when there is a shuffle, which means the data is moving across the cluster, and it's gonna be expensive, right? Because there are IO operations involved, and then it's gonna redistribute the data and perform the operation. So this is the simple way how you can actually imagine how the shuffle operation works. But we're gonna also understand this operation with a very simple example of the data. So again, we have a cluster here, Spark cluster. And now let's say we again have similar scenario with the node 1 having 4 partitions, node 2 is having another 4 partitions, and here, so here we have a good naming convention so you can understand clearly. So we got 8 partitions in total, partition 1, 2, 3, 4, 5, 6, 7, 8. Then we have data in each of the partitions. So if you see clearly, the key one is actually being spread out across the partition. So key one is available in partition 1, key one is also available in partition 3, and in partition 5, partition 7. So this is just to make you show how this data gonna be flying or redistributing across the partitions. Now, so we have the data in the cluster. Now let's say I apply a group by operation. So again, as I said before, group by gonna be copied to all the partitions or all the node because it's the parallel ecosystem, right? So I apply a group by operation. Then what happens? So once I apply the group by operation, Spark is gonna use something called default partitioner. So default partitioner in Spark is hash partitioner. So what it's gonna do, it's gonna identify, because if you see very closely, we are performing group by operation, right? So this group by operation needs same keys to be in the same partition in order to group by, right? So we need to somehow know key 1 should go to which partition, key 2 should go to which partition, and so on and so forth. So this partitioning function, which is the default hash partitioner, is actually gonna do the same thing. It's gonna calculate the partition number or the partition name, or to say the exact partition for a particular key value pair. So this algorithm gonna identify partition for each key value pair. So let's say we run this algorithm, I mean not we, Spark gonna run this algorithm, and let's say it identifies these partitions. So if you see in the white box, key 2 value 2 should go to P2, key 1 value 1 should go to P1, similarly key 3 should go to partition 3, key 4 should go to partition 4, then again key 1 to P1, and key 6 to P6, key 7 to P7, and so on and so forth. So now the moment I say do a group by, Spark gonna apply the partition function to identify which data or which row should go to which partition. This is done. Now once it identifies this, it's gonna do what? It's gonna serialize before sending, of course, because you need to move this data across the cluster. You cannot move it like an object, right? So this is where the serialization comes into play. So whatever data is there which needs to be transferred to another partition would be serialized, and to serialize, it's gonna do what? It's gonna put this data which needs to be transferred to the disk. So these white boxes that you see are disk, and the gray boxes are memory. So you see Spark gonna write it to disk as a temporary solution and then serialize it before sending it to the network. And then after sending it to the network, the receiving partition gonna deserialize it and then have it in its memory. So now we have partition 1 having all the key 1s, partition 2 having all the key 2s, partition 3 having all the key 3s, and so on and so forth. And now we apply the operation and we get the output, right? I hope this is clear. We're gonna just do a recap to understand the steps that is being done in the backend to have all this being computed efficiently. So key takeaways. Data movement. This is nothing but the recap of what we just saw in the simulation. So data movement: during a shuffle, data is moved between partitions and across nodes. Intermediate storage: Spark writes intermediate data to disk before transferring it over the network. This is needed because Spark needs to serialize the data before actually sending it over the network. Partition count: by default the number of partitions remains the same unless explicitly configured. So this is very important. So the number of partitions which were before the shuffle operation would remain the same after the shuffle operation unless you explicitly configure this in Spark configuration. Cost: so this is very important. This is the main topic, main reason why we are discussing this problem, right? The cost. Shuffle is expensive due to disk IO, of course, because it's writing to disk for a temporary period and reading it from the disk, doing serialization, deserialization. Network transfer, of course, because it's shuffle, it's going to transfer data, and overhead of creating new partitions. Yep. Overhead, serialization and deserialization, this is the main problem, so it's not the problem but main cause why shuffle operations are expensive and why they take longer, because you are writing it to disk, serializing it, moving it to another partition, and deserializing it, and then applying the operation. Now, why shuffle is expensive? I think by now you already have an idea why shuffle is expensive, right? But we'll just go through the bullet points very quickly. Disk IO. Writing and reading shuffle files to from disk adds significant latency. Of course, when you have any disk IO, there's gonna be a significant delay or significant change in latency. Network latency. High volume data transfers over the network can cause congestion and delays. Resource utilization. The shuffle process consumes CPU, memory, and disk resources, often creating bottlenecks in the cluster. Fault tolerance overhead. Spark ensures fault tolerance by persisting intermediate data, which increases the shuffle's storage and compute overhead. I think this you already understood. I don't have to explain you very deeply because of the simulation, right? Because you see there are so many operations involved. It's not just moving the data. It does a lot of work in the backend to move this data and have the calculation done. So in general, shuffle is expensive. Now we already talked about what is shuffle, why it's expensive, and why it happens, right? So now let's talk about its mitigation strategy. What you can do to minimize the effect of shuffle. Use reduce like operations. So this is the first recommendation that I would be suggesting you to do if you ever encounter a shuffle problem, or you would be encountering the shuffle problem for sure. So instead of using operations like group by key, prefer reduce by key or aggregate by key whenever possible. These operations perform partial aggregations locally, reducing the amount of data shuffled across the network. So you can imagine, so group by key is actually bringing all the keys to the same partitions as we just saw in the simulation, but reduce by key or aggregate by key actually does the partial aggregation in the partition itself, and then it actually transfers the data across the network. So the amount of data that would be shuffled in the reduce by key would be way lesser than group by key. There would still be a stage called exchange, which is nothing but signifying that a shuffle operation is happening, but the amount of data would be way lesser than in group by key operation. And if you see on the screen, we have a simple example showing how the same thing can be done in two different ways. So in the first example, we do df.group by on customer and get the total amount. And in second also, we do the same thing but using reduce by key. So it's literally same, but actually make a lot of difference in the backend. Second thing that we are talking about now is use partitioning strategically. So this is very important and should be kept in mind while dealing with shuffle problems or big data Spark problems. By default, Spark uses a hash partitioner, but you can control how data is partitioned to reduce shuffling. For example, if you know your data is skewed, use a custom partitioner to balance the load. So as you saw in the simulation before, Spark uses hash partitioner, which is calculating a hash for each key and a value pair. And this is by default. But if in case you know your data is skewed already, you did some data modeling or data analysis, or maybe you know somehow that your data is skewed, we suggest you to actually use custom partitioner. And you can actually create your own partitioner based on a class provided in the Spark library, which is called partitioner. So here is a small example showing the same. We are creating a custom partitioner which extend partitioner, and then you override number of partitions and get partition. And here if we see, what I'm doing is, if k is less than 10, we are saying move it to partition 0. If k is less than 20, move it to mid-range values to partition 1. If anything else, move it to partition 2. So I mean, this is just an example, not should not be replicated in real practice, but you can actually use your own partitioner when you think your data is skewed. Third suggestion would be to use coalies and repartition efficiently. If your data is heavily skewed or you are processing a small data set, use coalies instead of repartition to reduce the number of partitions without triggering a shuffle. So actually, if you know already, coalies is actually designed to reduce the number of partitions, while repartition is actually designed to increase or decrease the number of partitions. So coalies is actually an operation which does not involve shuffle. So if you do a coalies, it will not generate a shuffle, because what you do is you are merging the partitions. You are not transferring the data across the network. So it's very much advisable, if you have a small data set or if you think your data is skewed, you should use coalies, which will gonna decrease the number of partitions without shuffling. Another suggestion is to use broadcast join. For joins, use broadcast joins when one dataset is small enough to fit in memory. This avoids shuffling the small dataset entirely. So basically what happens when you have a small data set, we don't want you to move this data across all the partitions, right? It's gonna increase unnecessary movement of data. Rather, you can broadcast this small data set, which is nothing but copying this data set on each partition, so Spark does not have to look for this data anywhere else in the cluster. And this is very important when you have a small data set on one side and a big data set on the other side. This is a very typical scenario where you are joining the reference table or the small dimensions with your fact table. We recommend using broadcasting the small dimensions or the reference tables. Last but not the least, increase shuffle memory. So, in general, we do not recommend you to use shuffle memory too often or as a first step solution, because this is something that is that's like an ICU thing, right? When you have nothing, you just go in the emergency room to look for the solution. So this is nothing but kind of thing that you can go and play around if you try all the other options which are mentioned before and did not get lucky enough to optimize your job. There are mainly two properties that we suggest you can do or you can fix. One is Spark Shuffle File Buffer, and another one is reducer.max size in flight. So these you can tune in, but again, not advisable to try it first. First, try to understand why it's happening, why you actually need to make changes in this configuration, or if there is need be, then only go into making this configuration. As of my personal experience, I never change these properties, and because usually you can solve the shuffle problem from the methods that I just explained you before. Now, in order to summarize everything what we discussed until now, use reduce like operations, use reduce by key or aggregate by key wisely. Use broadcast join when one dataset is small, always broadcast it. Use custom partitioning or coalies. If your data is skewed or too small, always use coalies. Tune configurations. Last, but always use them precisely and only use it when other options are not working. So this is all for today's video. I hope you find some insightful things about shuffle problem or Spark in general. If you really loved this video, give it a thumbs up and subscribe for more such videos. In next video, we would be talking about a serialization and how it affects the Spark performance. So stay tuned and see you next time.